Hi everyone. So again, we are into our second part of our matter and change chapter. So we're just getting some more definitions that you have to remember and some of those fundamental basics. So we were talking about state changes last time. Or we were talking about states like solid, liquid, gas, plasma. But now let's talk about how we work with transition phases. So transition phases are just going from solid to liquid, solid to gas, things like that. You have to know what those are. So there are 5 of them. Or 6 of them, sorry. We got solid to liquid. Solid to liquid, you might be able to guess what that is. That's just going to be melting. Okay, so ice going to water, things like that. We have liquid to gas. You might be able to figure that one out as well. Liquid to gas, right? Water to water vapor. We can call that, you might say boiling, but we call it evaporation. It's more scientific. We got gas to liquid. Think about what that could be called. Gas to liquid, like when you're taking a shower and it steams up and it makes the mirror all foggy, that's called condensation. Or when you're drinking a cold glass of water on a hot day, or tea, since we're in the South, I guess. Okay. Liquid to solid. You can figure this out. Liquid to solid, right? We could call that freezing. Some of you might have thought solidifying, but freezing is more the term we use. These are ones that you might not know. Gas to solid. Gas to solid. Okay, so we're skipping that liquid phase altogether and we're going straight from gas to solid. This is called deposition. Okay, you might be thinking, what's an example where it goes from gas to solid? The best one that I could think of is frost. Okay, when it gets really, really cold, that fog or that water vapor in the morning just turns straight to ice on your windshield. Okay, frost. Next thing, solid to gas. So we're skipping right over liquid again, and we're going from solid to gas, and that is called sublimation. Sublimation, solid to gas. Okay, and the best example of this is dry ice. Okay, if you ever see dry ice, it looks like just a big solid block of ice, but it looks like kind of steam or fog is coming off of it. Okay, that's just sublimation. That dry ice is solid CO2, and it really wants to be in a gas state. We just make it really, really cold, so it's this block of ice. But then when we set it out at room temperature, it wants to be a gas so much that it just turns instantly to gas without turning to that liquid phase. All right? So those are our transition phases that you need to know about. Next thing, I kind of talked about this, I think I just said the word just briefly in our last video. We have to talk about colloids, okay? Colloids are kind of mixtures of states within themselves. I think I said that people say there's like 25 states of matter or whatever. They're pretty much talking about colloids, okay? These are mixes of states of matter. So again, these are just things that you're going to need to know. Some definitions. We got our first one, which is aerosol. Okay, this is a liquid in a gas. Okay, aerosols are liquid in a gas. You can probably think of some off the top of your head. Some I think of right off the bat are hairspray. Okay, hairspray. Right, you spray that. It's kind of a mist. It's a gas, but there's little droplets of liquid in there. Next one, foam, which is gas in a liquid. Right, foam, shaving cream, okay, it's a liquid form, but there's little gas bubbles in there, so that is a foam. The next one would be a sol. Okay, this is a solid and a liquid. There's little bits of solid and liquid, you can't see them. An example of this would be paint. Okay. It is a solid, but then when it dries, all that liquid evaporates and the solid remains. Okay, another example of this is pine sol. That's why they call it pine sol. There's little bits of solid in that liquid cleaning stuff. Okay, the next one we're going to say is gel, which is a liquid and a solid. Okay, so it's in solid form, but it could be very liquidy. An example of this is butter. Okay, it's a solid, but it's got a bunch of liquid in there. It's just solidified. Okay, so look at a solid hair gel, right? That's why they call it gel. And the last one is solid foam. Another example of gel would be cheese, which is kind of weird to think of cheese as a gel, but that is also a gel. Solid foam is a gas and a solid. So it's this solid, but it's got little gas bubbles in there, and our best example of that is styrofoam. Okay? So these are just things that you have to memorize, those transition phases and those colloids. Okay, kind of a pain, but they're good things to know if I bring up sol gel or aerosol or sublimation, that you know what I'm talking about. Next thing we have to talk about here are types of changes in chemistry. We have two types of changes, and we've probably dealt with this before. We have physical change, and we have chemical change. Okay, so in physical change, chemicals aren't changing, okay, they're just changing form. So molecules are just moving around, getting closer together. So kind of like in our transition phases, those are known as physical changes, okay? So this just results in a rearrangement, I think I'm spelling that right, of molecules. Okay, these are things like water molecules being spread out if they're in a gas vapor, and then getting closer together if they're liquid, and then becoming really close, or spread out, I guess, with ice, when they change into a solid. All right, so these are rearrangements of molecules. These are physical changes. Okay, I also like to describe them as easily reversible. Okay, you could easily melt ice and then freeze it again. Okay, that's how you know it's a physical change. But chemical changes, okay, chemical changes are results in formations of new substances. So that's where we're mixing chemicals together and they're actually changing into something new. Okay, that's like when we ignite gasoline. Okay, it is changing from gasoline and oxygen to CO2 and H2O, right? So let's give a couple examples of a physical change. Cutting potatoes. Okay, they're still potatoes. I just cut them up and rearranged the molecules, separated them out a little bit. Okay, another example of the physical change. Boiling water. Right? Again, I'm just spreading out those water molecules. I'm not changing them into something new. Another one. Let's go to chemical change now. Rust. Rust is a chemical change. And some of you might be saying, well, I could grind rust off of rusted stuff and it looks new, like it's reversible. No, you're just getting rid of all the oxidized iron molecules, okay? So that is a change. You can't unrust something. You could scrape it off and make it look newer, but it's still a chemical change. Those molecules are just now in the ground because you grinded them off, okay? Burning gasoline. As an example, if you can unburn gasoline, you got yourself a $1 billion idea. Okay, but burning gasoline, you can't reverse that. And then food rotting. That's changing the chemical makeup of the food and change it into something totally different. Okay, so again, physical, we're just rearranging the molecules. Chemical, we are changing it into something new. So let me just draw a molecular representation of this. Molecular representation, we're just zooming in at a particulate level. So again, I might have some oxygen molecules here, okay? And say I'm just bringing them closer together. So I might have gaseous oxygen here, and now I'm just bringing them really close together. I've made them really cold, or I've put them under immense pressure. That is just a physical change, okay? They are still oxygen molecules. I've just rearranged them a little bit. And for chemical change, I might have something like water, right? H2O. I got these two hydrogen, this oxygen molecule, okay? H2O might like to be decomposed into H2 and O2. So I'll have some hydrogen and some oxygen chilling around here. Let's see how many I can get moving around. Okay, so this is a chemical change. I have broken bonds and made totally new chemicals. I've gone from H2O to just hydrogen, H2, and oxygen gas. So this is what happens at a particulate level, at a zoomed in level. Let's do a couple examples, okay? Let's do a popsicle freezing. Okay, physical or chemical. Can you undo this? Yeah, right? It's not turning into a chocolate bar or anything like that. It's still a popsicle. It's just freezing, or it's frozen now. So this is physical, right? Milk going sour. Right? You can't unsour milk. It is now going through a chemical process. It has spoiled. It's definitely not milk anymore. It's something gross. That's a chemical change. Lighting a match. That is a chemical process called combustion. Okay, you can't unlight a match. They're taking that oxygen and turning it into CO2. You're igniting it, so that is chemical. Butter melting on toast. It's still butter, right? It's just melted now. So that is physical as well. Let's give you one more. Let's go with molding clay, right? If I take clay and I mold it into a shape, I could unmold that. I haven't changed it. After I mold it, it doesn't turn into stone, right? It's still clay. So that is a physical change, right? Let's keep going. We got something I like to call the matter pyramid. So matter, as we talked about before, makes up everything, but I would like to break it down a little bit so that we can understand it or classify it a little bit better. So matter, I will split it up into two things. I will split up into pure substances and mixtures, okay? Pure substances and mixtures. And then I will take it even a little bit further. I will split up those pure substances into things like elements, which are our atoms on the periodic table, and into compounds, which are our H2O, CO2, H2O2, NaCl, FeSO4. Okay, those are just mixtures of elements, okay? Yeah, they're a mixture of elements, but we're still going to count them as pure in the greater scheme of things, okay? And then mixtures, we have two types. We have homogeneous and heterogeneous, okay? So we have homogeneous and heterogeneous. So what I'm going to be asking you a lot is this a pure substance? Is this a mixture? What type of mixture is it? Is it homogeneous or is it heterogeneous? What kind of pure substance is it? Is it an element or is it a compound? So let's dive into these a little bit more. Pure substances are easily defined as just the same throughout. Okay, they're the same throughout. There's no like anything in there that kind of makes it impure. A pure substance is just the same throughout. And our first category on those pure substances were elements, which again are just atoms, right? They're those little Jimmy Neutron looking figures. Okay, elements are just atoms, and I've given you some examples of that before. Okay, we got carbon, we got gold, AU, we got H2, even though it's two of them, it's still a pure substance. Hydrogen, you just never see it by itself. Okay, so that's still an element. So let's give you one more. Let's go with phosphorus. Okay, and then compounds. Compounds are just defined as bonding elements together. Okay, we got things like H2O, which just means I have two hydrogens, one oxygen, right? That means I got one oxygen, two hydrogens there. I got things like CO2, which means I have one, let's say, carbon and two oxygens. Okay, and then let's go with O3. O3, which is, does anybody know? It is ozone. Okay, ozone, which is just three oxygen. Okay, so those are compounds. Those are more than two elements mixed together. Actually, I don't like that because you can count that as an element almost because it's all the same throughout. Let's go with another one. Let's just go with hydrogen peroxide, okay, which is what you put on your cuts. That hydrogen peroxide is extremely corrosive. What you guys use is like 3%, so it just burns a little bit. But if you get something that's like 40% or 60%, it'll eat your skin off. Okay, so that's hydrogen peroxide. These are compounds. These are mixtures of elements. Okay. Now let's get to the other side of our pyramid and let's break that down. Those are mixtures, which I'm just going to define as not the same throughout, okay? Or made up of multiple substances. That's a better definition, okay? Made up of multiple substances. And we got those two types of mixtures, which is homogeneous, okay? And heterogeneous. Let's talk about homogeneous. Homogeneous, we're going to say, is the same throughout. Okay, the same throughout. A mixture that doesn't have chunks of stuff in it, but it's still a mixture. Things like Kool-Aid, things like steel, and things like Gatorade. Okay, when you look at those, there's no chunks of stuff in their Kool-Aid. Hopefully there's no chunks of stuff in your Kool-Aid or Gatorade. Gatorade, which is just Kool-Aid with salt in it. And steel, same throughout. There's no like chunks of gold or anything like that. That's a homogeneous mixture. But a heterogeneous mixture is something that is, I'm just going to say, not the same throughout. It's a mixture that's not the same throughout. Okay? So, we're talking things like pizza, right? That's a mixture. It's just got a bunch of stuff in it. That's not the same. It's not just a bunch of cheese, right? It is a mixture of dough and toppings and things like that. Let's go with Italian dressing. right? If Italian dressing, if you let it sit, it separates out, so that's not like a pure mixture throughout. Things will fall out of it. And one not so common one that you might not think about is sour cream, right? Every now and then you get sour cream out, it's got that stuff sitting on top, you gotta mix it back up again, okay? So that is also a heterogeneous mixture. So let's do a couple examples real quick. Let's go with rainwater. Rainwater doesn't have really chunks of things in it, so we're going to call it homogeneous. Okay. Things like, let's go with paint. Okay, paint, same throughout. Okay, it doesn't have big chunks, all right, or else when you put on your wall, there'd be bits of different color in there. So we're going to say that's homogeneous. Soil. I'm talking like if you went outside and dug a bunch of soil out of the ground because you're an animal, and you might get some rocks and worms in there. So that's going to be hetero. And let's do one more, and then we'll move on. And let's go with a taco. Okay, taco. Right, it's not the same throughout. That'd be weird if it was just a glob of stuff that tasted like a taco. So it is hetero. All right. Last bit, I promise, and then we'll be done with our intros to this chapter, right? Just a few more definitions, and we are done. Extensive versus intensive properties, okay? Extensive versus intensive properties, okay? Intensive property is any characteristic not dependent on mass, okay? Or any property not dependent on mass. So this is a characteristic of something that doesn't change due to the mass, okay? I'm talking about things like color, okay? If I have a red balloon and I change its mass, fill it up with more air, okay, the color is not gonna change, it's gonna stay the same. So the color is not dependent on mass. Another thing is density, which we'll talk about more later, okay? If I have a drop of water or a cork, a little piece of cork, it floats, it has the same density. If I get a huge cork, it's still going to float, okay, no matter what size it is. So density always stays the same no matter if you change the mass or not, okay? The way I remember this one, intensive property is not dependent on mass. You got not in here, and intensive has an N and a T, okay? That's just how I remember it from extensive property, which is just the opposite. Which is any property dependent on mass, or any characteristic dependent on mass. So things like weight, volume, okay, length. So if I change the mass, these properties are going to change. So with weight, volume, length. If I add more atoms, right, if I add more atoms to it, it's going to change that property. It's going to change the weight. If I add more atoms, the volume is going to be bigger. If I add more atoms, it could change the length. So these are extensive properties. Intensive properties, if I add atoms, it's not going to change it. If I add the same atoms, it's not going to change the density. If I add the same atoms, it's not going to change the color. Okay? Almost there. Separation. All right, we're talking about separating mixtures. First one, there's only two. Separating mixtures, distillation. Okay, distillation helps us separate a liquid from another liquid. Okay. Here's some examples of this. Okay, moonshine, right? That's how they make moonshine. They evaporate. They got this big vat of liquid that has alcohol in it, and they heat it up, and the alcohol evaporates out, and then it condenses, and then they make moonshine. Another example is oil refineries. Okay, when they get oil, the ground's just this big, nasty glop of stuff. They have to evaporate out the jet fuel, the gasoline, the diesel, and then after they evaporate for a while, at the end, they're just left with that asphalt, which they use on roads. And then let's talk about the next one, which is filtration. So again, distillation, liquid from liquid. Filtration is separating a liquid from a solid. Okay, examples of this: coffee, right? You got your coffee filtration. You're getting that liquid through those coffee grinds. You're making sure none of that solid coffee grinds go through. Okay, so filtration, coffee. All right. Sometimes if you go to the beach, you got those little filters where you can put sand, and the sand will go through, or the liquid will go through, but any nice solid chunks of shells or anything will stay in that little strainer. So those are two separating mixtures. And one more thing. Chemical reactions, which we'll deal with this a lot. Okay, the only thing I want you to know is just kind of the naming of chemical reactions, how we name these things. So, say I have something like HCl, which is hydrochloric acid, NaOH, which is sodium hydroxide. It's going to make H2O and NaCl. So, what this is just a reaction equation that you'll see. This arrow is pretty much just telling you of what's it's going to become something. So this HCl, this NaOH is going to combine together, that plus sign, and it's going to become water and salt. Okay, so anything on the left side are our reactants. They're the things that reacted together. Everything on the right side are called our products, okay, things that we produce. And then this is just our reaction symbol. You will see me write reaction as RXN, just to shorten it up. So reactions I might put as RXN. Okay, so that is just the nomenclature for reactions. You got dangerous chemical of HCl, which could dissolve skin. NaOH is a strong base that could dissolve skin, but when we combine them together, we make nice, unharmful products of water and salt. Okay, so that is our intro to this chemistry terms. Have a great day.